Welcome back to Mr. Vaughn's classroom. Please take a moment, hit the subscribe button, and give this video a thumbs up. This lesson looks at Unit 5, Introduction to Exponential Functions, Lesson 4, Understanding Decay. Our learning goal today is to look at exponential decay. We have 3 learning targets in this lesson. As we work through the practice problems, keep these in mind, and if at the end of the lesson you don't understand any of these learning targets, please drop a comment below and I'll get back to you with any clarification I can offer. Learning target number 1 says I can use only multiplication to represent decreasing a quantity by a fraction of itself. What they mean by that is instead of dividing to make it shrink, what you can do is you can multiply by a fraction, and that is essentially the same thing as dividing. So by thinking of it as multiplying by a fraction rather than dividing, it allows us to write it the same way we did before, and it allows us to notice whether we are multiplying by a number that is greater than 1 so that we are growing, or if we're multiplying by a number less than 1 so we're decreasing. So that's what they mean on this first one. Learning target number 2, I can write an expression or equation to represent a quantity that decays exponentially. So they just want to make sure that the same format we used in the previous lesson to write exponential equations, you understand that you can write using that same format, only understanding that your growth factor this time is going to be a fraction that is less than 1, causing the decay. And then learning target number 3, I know the meanings of exponential growth and exponential decay. So making sure that you understand exponential growth means your growth factor is greater than 1, so it's increasing your result every time, and you're going to have that steep curve upwards. Exponential decay, on the other hand, is multiplying by a growth factor that is less than 1, so your amount is actually getting smaller each time, and you end up seeing that steep curve downward. We have one glossary term for this lesson, and that is growth factor. In an exponential function, the output is multiplied by the same factor every time the input increases by 1. The multiplier is called the growth factor. And don't let the name confuse you. Whether you are increasing or decreasing, it is still called the growth factor. The difference is that that growth factor is either greater than 1, causing it to increase, or that growth factor is less than 1, causing it to decrease. Our first practice problem says a new bicycle sells for $300. It's on sale for 1/4 off the regular price. Select all the expressions that represent the sale price of the bicycle in dollars. So let's look what each one says. A has 300, which is the price, times 1/4, which is the discount fraction. If we multiply the price times the discount fraction, what we're going to get is the discount amount in dollars, not the actual sale price. So it's not A. Now let's look at B. B has 300, which is the price, times 3/4. So we have to think, where does this 3/4 come from? Well, if multiplying it by 1/4 gave us the discount amount in dollars, then multiplying it by 3/4, we're multiplying it by the amount that still has to be paid. So the 3/4 is the fraction to pay. And what that's going to give us is the amount to pay in dollars. So B is a correct answer. One way that we can find the actual sale price is to multiply the original price times the fraction that we still have to pay after the discount. So now let's look at C. Again, we have 300, which is the price. Then it says times 1 minus 1/4. Well, 1 minus 1/4 is 3/4. And all that does is turn it back into B. So that's price times total fraction, which is the 1, minus the discount fraction, and when you do that, it's going to give you the fraction to pay, which means this is going to give you the amount to pay in dollars. And that's what we're looking for, the sale price, the price that we're going to pay after it's been taken. Now we look at D. D has 300, which is the price, but now it says minus 1/4. Well, if you subtract 1/4, that's actually all that you're doing. You are subtracting 25 cents. And that gives you $299.75. That is not the sale price. This doesn't mean anything. So it's not D. And our final choice is E. And this says 300, which is the price, minus, because of order of operations, we would do this multiplication first. And if I multiply 1/4 times 300, if you think back to A, we said that was going to give us the discount amount in dollars. So now if I take the original price and I subtract the amount in dollars that they're going to discount it, what that will leave is the sale price. in dollars. And that is what we're looking for. So B, C, and E are all methods to find the sale price. A and D are not. If you have any questions about this practice problem, please drop a comment below and I'll get back to you with any clarification I can offer. Our next practice problem says a computer costs $800. It loses 1/4 of its value every year after it is purchased. Number 1, complete the table and show the value of the computer at the listed times. So, when we start out, the time in years, 0, means when it is bought. So that would be the $800 starting price. Now, what we need to notice is that it loses 1/4 of its value. If it loses 1/4 of its value, then it keeps 3/4 of its value. So what we're going to do, each time we add a year, we're going to multiply that value by 3/4, or if I want to put it into a calculator, 3/4 is the same as 0.75. So we're going to take a calculator and we'll say 800 times 0.75, and that equals 600. So that means after 1 year, it still has $600 of value. Now, to go to the next year, we're going to take that $600 and we're going to multiply it by the 3/4 of its value that it still has. And that leaves $450 of value. And then we add another year, so we're going to take this $450 of value that it still had, and we're going to multiply that by the 3/4 of its value that it keeps after it loses another 1/4 of its value. And that brings us down to $337.50. Now, the last one says, what if we don't know the number of years? So, in order to do that, we would be starting with the $800 purchase price. We would multiply that by the 3/4 of its value that it maintained each year, because it was losing 1/4 of its value. And then our exponent would be t. Now we would be able to take the number of years, substitute that in for t, and now we would be able to find out the value after any number of years. Number 2, write an equation representing the value v of the computer t years after it is purchased. So, we're going to say v is the name, because that's what they told us to call it. equals, and all we're going to do is take this bottom expression that we just created, and that will be the rest of the equation. The value equals the $800 starting price times the 3/4 of its value that it keeps each year after losing 1/4 of its value after each year, and that 3/4 is to the power of t, the number of years after it was purchased. And now number 3, use your equation to find v when t is 5. What does this value of v mean? So we're going to say v equals 800 times 3/4 to the power of 5. Now I can bring up my calculator and I can say 0.75, which is the same as 3/4. And now I want to use this button here that says x to the power of y. That will let me use an exponent larger than 2. I press this button, and now if you notice up here, I have the little up arrow, and now I can type in the number of years as 5. And that will give me 0.23 and so on. Now I would take this and multiply it by the $800 starting price. And that gives me $189.84 when we round it. So you want to not round until you get to your final answer. That way it can be as accurate as possible. And the reason that I'm going to use the 3 to tell me how to round the 4 is because we're talking about money, so I only want 2 decimal points. So that answer was 189.84. And they want us to explain what this value means, and what it means is the computer still has a value of $189.84 5 years after it was purchased. And if you want to see whether or not this is true, remember we said after 3 years it had $337.50. So if I multiply this by the 0.75 to get to the 4th year, I'm down to $253.13 if I rounded it. And now if I multiply the 4th year value by 0.75 to get the 5th year value, there I get my answer of $189.84. So understanding how to write the exponential function will allow you to go straight to the answer without having to repeatedly multiply by the fraction that you're keeping. If you have any questions about this practice problem, please leave a comment below and I'll get back to you with any clarification that you might need. Our next practice problem says, a piece of paper is folded into thirds multiple times. The area, A, of the piece of paper in square inches after n folds is A equals 90 times 1/3 to the power of n. Number 1, what is the value of A when n equals 0? What does this mean in the situation? So the first thing you need to understand is that anything to the power of 0 equals 1. So for number 1, A equals 90 times 1/3 to the power of 0 becomes 90 times 1, which equals 90. And what this means is the area is 90 square inches before it's been folded. Because if n equals 0, then that means there are no folds yet. Number 2, how many folds are needed before the area is less than 1 square inch? So to answer this, I'm going to make a table. N is my input, and A of n is my output. So we already know that when there's no folds, the area is 90. If there is one fold, then we have 90 times 1/3 and that equals 30. Now, if we fold it a second time, we take this 30 and we multiply it by 1/3. And now we have 10. If we fold it a third time, we take this remaining 10 and we multiply it by 1/3. And we're down to 3.3. Now, if we fold it a fourth time, we take this remaining 3.3 and we multiply it by 1/3. And now we have 1.1. So we're almost there, but not quite, because they said they wanted it less than 1 square inch. So now we take this remaining 1.1 and we multiply it by 1/3 and we get 0.37, which would round to 0.4. So it takes 5 folds before the area is less than 1 square inch. And number 3, the area of another piece of paper in square inches after n folds is given by b equals 100 times 1/2 to the power of n. What do the numbers 100 and 1/2 mean in this situation? So remember that an exponential expression has initial amount times the growth factor to the power of the input. So the 100 is the initial amount. Area of paper before any folds. The 1/2 is the growth factor. So that means that is the area of paper remaining after each fold. So in the first example, when it was 90 times 1/3, we had a paper with an initial size of 90 square inches, and every time it was folded into thirds, it still had 1/3 of its area remaining. This example in number 3 starts out with an initial area of 100 square inches. It is being folded in half each time, so it keeps 1/2 of its area after each fold. If you have any questions about this practice problem, please leave a comment below and I'll get back to you with any clarification I can offer you. Our last practice problem says at the beginning of April, a colony of ants has a population of 5,000. Number 1, the colony decreases by 1/5 during April. Write an expression for the ant population at the end of April. So, first we need to understand that if it decreases by 1/5, it keeps 4/5. And we need to remember that exponentially we write initial amount times the growth factor to the input power. So, for number 1, I know that it begins with a population of 5,000. And I know I'm multiplying by a growth factor of 4/5. Because that's how much of the population it keeps if it loses 1/5. Number 2. During May, the colony decreases again by 1/5 of its size. Write an expression for the ant population at the end of May. Well, this would be the initial 5,000 population times the 4/5 of the population that it kept in April and the 4/5 of the population that it kept in May. But now we need to make this 4/5 to the power of 2 because this has happened for 2 months now. And number 3, the colony continues to decrease by 1/5 of its size each month. Write an expression for the ant population after 6 months. Well, it still begins with that initial ant population of 5,000. But now we need to continue multiplying by that growth factor of 4/5, but the exponent now needs to be changed to 6 because it's been 6 months that this population has kept 4/5 of its population each month. If you have any questions about any of the practice problems we did in this lesson, please leave a comment below and I'll get back to you with any clarification I can offer. To finish up this lesson, I want us to go back and review the learning targets. Number 1 learning target, I can use only multiplication to represent decreasing a quantity by a fraction of itself. So if you understand how to multiply by the fraction that's remaining in order to set up your exponential decay, then you are right where you need to be. Learning target number 2 says I can write an expression or equation to represent a quantity that decays exponentially. So if you understand that it is initial amount times the fraction that's remaining to the power of the input, then you're right where you should be. And learning target number 3, I know the meanings of exponential growth and exponential decay. If you understand that exponential growth is when you're multiplying by a growth factor greater than 1, and if you understand that exponential decay is when you're multiplying by a growth factor of less than 1, then you're right where you should be. If you still have any questions about any of these 3 learning targets, please leave a comment below and I'll get back to you with any clarification I can offer. I look forward to seeing you in the next video. Please take a moment to hit the subscribe button and leave a like if you found this helpful.